All right, let's get started. So yesterday we did we solved some exponential equations. Today we're going to sort of extend that a little bit, and we're going to solve logarithmic equations. They're not that much different. I'm going to give you sort of one little piece of information, and we'll solve a few, just so you can see what it's like. We will do the mastery test again. I'll hand them back. We can take them up afterwards, and then do them again. You'll see. No. So the one thing that I'm going to write down now might seem very obvious to you. And I think it will be obvious, which means that there won't be a lot of thought that has to go into this. But I can almost guarantee that a whole bunch of you at some point will get to an equation. You'll say, where do I go from here? That's when you think back to this little tidbit of information. It's obvious when it's spelled out, but when it's sort of masked in an equation, it may not be so obvious. So if log m base a is equal to the log of base a, choose any base, doesn't matter what it is. What has to be, yeah, sure. Yeah, both of the bases here have to be the same. So a has to be the same value. Then m has to equal n. Right, if we're looking at the, yeah, makes sense, right? And yet, for some reason, it's one of those things that as you're solving your equations, you get so buried in kind of what's going on, you kind of forget this. So that's why I explicitly wrote it down. We'll do a couple of examples of solving logarithmic equations. Some of the examples will use this fact, and others we're going to say, hey, we don't really know where to go. So what we'll do is we'll just turn the equation into an exponential equation and then solve it from there. So let's try a few. No, there could be numbers.
Yeah, but there has to be one variable, right?
Sure. Yeah. Yeah, I mean.
You can't just say log a 3 equals log a 5.
Right. Yes.
Unless you're trying to find it.
But you can't have the two values be equal then, right? Because if it's the same base. Yeah. I see what you're getting on. Let's try that again. So here's an example. Somebody asked this the other day, and I hope you don't think I was ignoring you. I don't even remember who asked it. Asked it, what if we're trying to find the base? We weren't quite ready to get to that point yet. I think we're there. I know we're there now. So here we need to.
Mr. Bonisdale, please call extension 3315. Mr. Bonisdale.
In this case, what we want to do is we can easily change this to exponential form. And when we change this to exponential form, what does that look like if we try to change this to exponential form? X to the negative 2 is equal to 0.04. And I'm going to do a little bit of work here without a calculator just because we can. This is the same as 4 over 100. Is that okay? 4 100ths? Is that okay? Everybody's sort of happy with that? Sure. Hey, yeah. We could do that. No, we need, so if we want to make that exponent positive, it has to look something like this. Where do we go from here? Do a couple of things. Sure, you can multiply. What do you mean flip both sides? Sure, yeah, we could do that too if you want. Nope, because we're flipping both sides. So we're allowed to sort of flip the one side, but if we do that, we better flip the other side. Oh, okay, sorry, I didn't mean to misunderstand you there. Yeah, we want to find x. So the next step is the square root. Take the root. Now, typically, when we take the square root, there would be a positive answer and a negative answer. We'll come back to that in a minute. Well, let's finish this off first, and then we'll come back to that.
So should we always turn the decimal into a fraction right away?
I mean, this was an easy one, and in fact, I chose 0.04 because we could easily write it as a fraction, but not only could we easily write it as a fraction, but we can also easily take the square root. So in this case, it's really easy to do this. You could, or you could do the square root of 100 divided by the square root of 4. Your answer is going to be the same. 100 divided by 4 is 25. The square root of 25 is 5. No, but I want to talk about why it's not plus or minus. When we take a square root, the answer, there is a positive answer and a negative answer. But I wanted to go back here. Sorry, say that again? Right, so Les is pointing out the fact that if we look at the graph of a logarithmic function, it looks sort of like this. The domain of the logarithmic functions are all positive values for x. And I know Leslie was asking about that earlier today, so I wanted to kind of just point out what's going on here. We're right that the result here, the domain for this log function can't be negative, but is it possible for the base to be negative?
Sure, why not?
Sure. So let's just kind of check it. Let's look at plus 5. If the base is 5, 5 to the negative 2 should equal 0.04. Yep. Does that work? Try that on your calculator here. Just make sure we're not going crazy and make sure we did this right.
Yeah, that's fine.
Okay. Now, what about this? Does this work? Does it work on your calculator? Awesome. So it's okay to have a base that's negative or a base that's positive. It's not okay to have the domain of the log function be negative, because if you look at the graph, you can see that that's not possible, right?
Would it be negative if the exponent was 3 instead?
Yeah.
But I don't get, so it's not negative 5 or negative 5 is equal to x. But it says x can't be.
You just said x can't be negative.
I said the domain. This isn't, remember that this isn't the domain of the function. These are the x values. Yeah, we use the variable x here, but this represents the base of the function. So our base can be negative, but
So it is plus minus 5.
in this case, it's plus or minus 5. So,
You said it wasn't negative.
Yeah.
well, I said we'll come back to it and have a look at it, because there will be some cases, not for the base, but for some of the values that we're finding where we say, hey, wait a second, x, whatever we're solving for, can't be negative. If we were solving an equation here, we wanted to find the domain of a log function, well, the domain of a log function can't be negative. And that came up in the homework the other day. I think it was it 2 days ago? I'm not sure how many of you got to that question, but a few of you asked me about why that was the case. So I wanted to highlight that because that is an important idea. Leslie?
The base and the exponent can both be a negative number, but just the product can't be.
Sure. Right.
The product that's in the.
So
I understand.
why don't we come back to that after? Well, I think I have another example that I can show you that why it can't be negative, and I'll show you why. Is that okay? Because obviously here it works, right? We checked positive result, negative result. We got the same thing. Sure. Yeah. Yeah. Yep.
But if it wasn't negative 2,
Okay. All right, let's move on to the next example. So let's try the log of 3x minus 5 base 7. And equals the log of 16 base 7. So this would be a situation where we have this setup, right? We have the log on both sides. The bases are the same. So the only thing that's different in these two equations is what we're taking the log of. So those two things must equal each other. And now we can solve this equation. And we get x equals 7. And that's just because of the fact that we're taking the log of some number on both sides. The base for the log is the same. So the only thing that's going to make these two sides of the equation any different is the value that we're taking the log of. So we can just set them equal because we know the left side and the right side are equal. Is that okay? I mean, this looks trivial, right? I mean, it kind of looks trivial, but it's one of those things that if you don't do it enough, you're not going to notice it. And I can almost guarantee that over the holidays, some of you are going to forget. Sorry, was that too fast? Some of you are still writing that down. I'll just wait a second until everyone's got it. That's good. So here's the log of 30x base 2 minus the log of 5 base 2 is equal to the log of 12 base 2. Again, our goal is to solve for x.
Can you do log? Can you say log to log of 30 minus log of 5? So 30 minus 5.
Very close. Yeah, so the bases are the same here. Remember that the quotient rule that we talked about the other day said this can just be simplified to the log of 30x divided by 5, and that has to equal to the the log of 12 base 2. Pardon me.
So then you can just go 30 divided by 5.
Yeah. So again, we're taking the log here, and the log here. The bases are the same. So the part that we're taking the log of parts that we're taking the log of have to be the same.
Why can't you just originally go
30x minus 5.
Because it's one of those.
Because the law doesn't say that we could just strip out. In fact, that's different from what we have here, right?
Yeah, yeah.
Leslie?
Can you just do 30 divided by 5?
No, because
Mm.
Why is it still a fraction?
Why is what still a fraction?
30x divided by 5.
Well, that's yeah.
Yeah, you can divide it.
Oh yeah, well, yeah. We're gonna get there. You're just ahead of me. That's all.
Well, why couldn't you do?
Oh, I could have done it here. Yeah, you're right. Sorry. Sure. Yeah, we can do. You guys are way ahead of me. That's great.
Why didn't I do it by 5 in the first place?
The division by 5 here happens as a result of this right here. One of the rules for dealing with logs said if we have the log of one thing minus another thing and the bases are the same, we can rewrite that as a single log using the division of those two things that we're taking the log of.
Is that one of the rules for
Yep.
down?
Monday maybe? Was that Monday? Yeah. And again, just like every other equation that you can do, that you solve, we should be able to take the two, plug it back into the equation and still get that the left side and the right side are the same. If we don't, then that means we probably messed up somewhere. Any questions so far? Let's try this one. So the log of x plus the log of x squared equals 12. Say that again? We can't factor in x, and the reason why we can't factor in x out here, remember that the log is a function. The function is being applied to x here, and the function's... You can't factor the log because it's not real. It's a function, right? So we can't just factor the log out. We can't factor out a log x because there's no log x here. It's a log x squared. No, you wouldn't. Because remember, this means take the log of x squared. Not just take the log of x and the log of x or so. It's not x times, it's, I see what you're saying. You're saying this, right? Is that what you're saying?
No, I'm saying take the whole log out, the whole thing.
But you can only do that. You can only do that if the second part looks like this. Then we could factor a log out of here and be left with an x. But that's different from the log of x squared. Remember, this means that the log function is being applied to x squared, whatever that is. We can't just strip one of the x's out of the argument of the log function. This is not the same as this. Why? Because this says that log acts on x times x, where this says that log acts on the x, and then we take that result and multiply it by x. Whereas this one means that the x squared gets the log applied to it. So these are not the same. But what we could do is we could use our laws of logs and say, hey, we have a sum. The bases are both the same here. They're unwritten, so the base is 10. The bases are both the same, so this becomes a single log with a base 10. And we're taking the log of x times x squared. Yeah.
You just add the exponents in this case, right?
Yeah, whenever you multiply powers with the same base, you would add the exponents for sure. That's probably helpful.
It doesn't become 2x, right? It's just x.
Yeah. What's weird?
If you think of like a sign, like that's a function, and you can add like that with a sign, you could add like a sign x3, but then you can't factor it into the sign.
You're saying this right here to go from here to here? Yeah, I mean it's one of the rules, and this actually comes from the rule for multiplying powers with the same base that allows you to add the exponents. That's if there were a log on the right, we could do that, but there isn't. So we're kind of stuck. Where do we go from here? Yeah, so if we get stuck and we're not sure where to go with these logarithmic equations, let's jump out of this log form and into exponential form. How do we write this as in exponential form? So the base is 10, the exponent is 12, and the result is x cubed. Yep. Yeah, we could do it that way too if we wanted to. Yeah. I think we would get the same result. We should get the same result. Do you want to see that? Is that helpful, or maybe I'll slide this over a little bit and maybe we'll come back to it. Let's continue along the lines here. So I'll do it in parallel here. So Jenna suggested, hey, why don't we pull this 3 down in front, which we could totally do. Might make the math a little bit easier, actually. Then we can divide both sides by 3. And then again, you're not really sure where to go, so we jump out of this log notation and into exponential. So 10 to the 4 is equal to x. So we kind of did the work ahead of time, whereas here, we're going to do the work after the fact.
Oh, you can just do the exponents in this case, so it's 12 divided by 2.
Yeah.
For the like the exponent form here, can't you just plug it into the 12 and then to the cube root?
Yeah. Yeah, sure. In fact, that's what we're going to do. We're going to take the cube root of both sides. How do we do that? Well, we need to take the cube root here, but we also need to take the cube root here. So the cube root of x cubed, and then we're going to do the cube root of 10 to the 12. Sorry, I lost my 3 there. And don't forget that the cube root just means to the exponent 1/3 with exponents to exponents, powers of powers, we multiply the powers together, we would get 12 times 1/3 is 12 thirds, or 4. Same answer, two slightly different ways to go about it. So 10 to the 4 means 10 multiplied by itself 4 times. What's that, 10,000? I'm happy to leave it as 10 to the 4, sure.
Want us to go through that process, or like I literally punched it through a calculator?
Literally punch what into your calculator?
Like 10 to the 4 is 10,000, right? No.
Yeah.
So why can't you use the 10 to the power of 12 and then cube root it?
Yeah, that's what we did.
Oh, you just wrote it out?
Yeah. John?
So in this case, we wouldn't have to do the cube root, like, because we could just use 12 divided by 3, which is 4, right?
Well, I mean that is the cube root, right? This part right here is the cube root. But you're right. You don't need to use the button on your calculator that says the cube root of.
So that'll work in every situation in this case, if it's x.
This worked out because we could divide 12 by 3 evenly, right?
Yeah, but if you can't,
If you can't, then you're going to have to go to your calculator, right?
okay,
Yeah.
you do it in the whole number.
Sure, yeah. Yep. I think there's just one left. Some of you are struggling a little bit with the rules for dealing with logs, so make sure you go back and have a look at the homework there, because that'll be important. This one's a little trickier. Yeah, so in this case, again, we have the two logs. The bases are the same. We're adding these two logs so we can write this as a single log. That is the product of those two values, the x plus 3 and the x minus 3.
Why did you do the product this time instead of the difference?
Because this was a plus sign. I can tell you didn't do the homework for that stuff.
Yeah.
You guys want to expand that?
That sounds like a good idea. I think maybe. Where if we didn't expand it, where would we go? And if we did expand it, where would we go next? Yeah, so if we expand this, we get a trinomial here, but then what would we do? I guess it would only be 2. Yeah, it's a difference of squares, right? So, but then where would you go if you had x squared minus 9 in here? Right, so we would kind of jump to exponential form. So you can either do the expanding now, or you can do it after the fact. You get to a point where you can't really go much further in logarithmic form, so we jump to exponential, and this just means that 2 to the 4 is equal to x squared minus 9. And now we can solve this as a quadratic equation. 2 to the 4 is 16. Is that okay? Don't forget, when we take the square root, we get a positive answer and a negative answer. Now here's where what I was saying earlier about making sure that you're checking what it is that you're finding makes sense. If x is -5, so maybe it's worth actually just doing a check. In grade 9, you probably call this a left side, right side check, where you check the left side and the right side, you plug in your value and see what you get. So let's go ahead and do the check. I'm going to do the check with -5. I'm pretty confident that the +5 is going to work, but let's have a look here with the -5. So we're checking to see if this is in fact true. Thanks. And this was all base 2. So going back to, I think John really wanted to know, why is it that we can't take the log of a negative number? And here's why. This means that 2 to some exponents, let's call it m, just to keep it totally different from any of the variables that we have on the board, has to equal -2. Is it possible for us to choose some exponent that when we put it into this equation, 2 to that exponent is going to somehow turn negative? So 2 to the -1, remember we could just make that a positive exponent by writing it like that. It's still positive, right? So there's no value for m that will make this equation true. This never works. So that's why we have to be careful with the negatives, is that we can't take the log of a negative number. And if you look at the graph of a log function, you'll see that I drew it earlier. The domain of the log function looks like this. We can take the log of any number greater than 0, but we can't take the log of any negative number. So in this case, we have to throw away the negative solution, and we have to say that x is just equal to 5. This example here that I did, we had a quadratic equation. It was a fairly straightforward one. There was no x term. You will probably see some that do have x terms. You might have to use the quadratic formula or factor. You'll get possibly 2 x values, one or possibly both could be negative. And if that's the case, you need to throw out your negative answers because we can't take the log of a negative number. Is that okay? Does that help clear up the whole negative logs of negative numbers? Okay. All right, so here's the work. It's on page 491. Well, there's a lot today. Sorry, Michael.
So then if it is -2, that's the result. If it's negative there, it can't work.
Right, we can't take, yeah, that's right. We can't take the log of a -2. So this doesn't work. Neither does this for that matter. It was a homework question from a few days ago, and I mean, that's kind of what we did here, right? This looks like a lot of work. Let me see if I can trim that down a bit. Unless you don't want me to. So for questions 1 and 2, let's just do every other question. So here we could do A, C, and E, because there are a lot there. Yeah. 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 Six and 7, we can just do A, C, and E as well. In fact, here, why don't we just do A, C, and E for all of these? All of these ones, 1 to 7 for sure. And then the rest are kind of one-off kind of questions without a whole lot of parts. So let's do that. You can do 3 if you want. There's no, well, I'll leave it. You could try 3. It's not hard. It's just one question. So, all right, let's leave it at that.